Okay, so for this video, we will be discussing integration by parts. So we are already in part 2 of integral calculus. So the previous parts were fundamental integration formulas, and the next part is the second part is the integration techniques. So integration by parts is already a part of integration techniques. Okay, so the integration by parts is a formula, okay, that is derived from the product rule. So if we recall the product rule for differentiation, so we have the differential of uv is equal to udv plus vdu. Okay, so that is the product rule, for differentiation. So what we did here is transpose vdu onto the other side. Okay, so that we will have udv is equal to d of uv minus v du. And then integrating both sides, so integral of udv is integral of udv. Then the integral of the integral of duv is uv, and the integral of vdu is integral of vdu. So we have this formula for integration by parts. So integral of udv is equal to uv minus integral of vdu. So what we actually do in integration by parts is we divide the integrand into u and dv. Okay, so the u part and the differential part. Okay, so once we have assigned properly what is u and what is dv, then we can apply this formula. So u v minus integral of v du. So if we assign u, so make sure that your u can be differentiated, okay, because it will be needed here, the differential of u. And if we assign dv, make sure that the dv can be integrated because we will need v in here, okay, in this part. Okay, so but how do we identify which part would be our u and which part would be our dv in the integrand? So we can be guided by the general rule in assigning u whenever we use integration by parts. So all we have to remember is this acronym. So LIATE. So LIATE, whatever. So however you want to pronounce it, as long as it's in order. So L stands for logarithmic, I stands for inverse trigonometric, A algebraic, T trigonometric, and E is for exponential. Okay, so it's decreasing order. Okay, so meaning in assigning u, we will prioritize the logarithmic in the assigning of u over inverse trigonometric. Okay, so the higher the most priority, okay, in assigning of u. So by the way, this is not the absolute rule but the general rule. So most of the time following this rule actually works. Okay, so say for example, so we have here integral of x cosine of 3x dx. Okay, so as you can see, we can't integrate this directly, okay, because so if we have the integral of cosine 3x, okay, its differential should be 3 dx, right? So if we have integral of cosine 3x, its differential should be 3 dx, okay, for us to be able to apply the formula for the integral of cosine. Okay, so we have here an excess variable. Okay, so if there is no x here, then we can integrate this directly. Okay, but we have an excess variable here. Okay, so that's why we can't apply directly the integral of cosine. Okay, so what we do if we have excess of a function or excess variable, so it is most of the time it can be solved using the integration by parts. Okay, so here we will assign our u. Okay, so it could be our u could be the x or the cosine 3x dx. Sorry, our x could be our u could be x or the cosine 3x. Okay, but using the general rule in assigning of u, then our u should be, we will prioritize the algebraic function. So x is most probably our u than the cosine 3x, which is trigonometric. Okay, so in assigning u, so we'll prioritize the algebraic function. Okay, so later after this, after solving this, so we will also try, what if we change the assignment. What if we assign our cosine 3x as our u? Then what will happen to the problem? Okay, so for here, our u is, we assigned as our x. Okay, and our dv, okay, so our dv from the formula, so our dv would be cosine 3x dx. Okay, so since we will also be needing du in our formula, then we will derive du. So du is equal to dx, derivative of x. Okay, so since we are given here with a dv and we will find v, okay, so then we will integrate dv. So what is the integral of cosine 3x dx? Okay, so first we should complete the differential. So it will become cosine 3x, its complete differential should be 3dx. Okay, so therefore we will write 1/3 there. Okay, so therefore v is equal to 1/3. Integral of cosine is sine. Okay, 3x. Okay, so in integration by parts, in obtaining the v, so we don't need to write plus c anymore in the integration. Okay, so because later on when we substitute v in the formula for the integration by parts, so the constant here will combine with the constant in the final answer. So therefore, the integral of x cosine 3x dx is equal to, so from the formula again, uv minus integral of v du. So our u is x, our v is 1/3 sine 3x, okay, minus integral of v and then v du. So our du is dx. Okay, so therefore we'll have here 1/3 x sine of 3x, okay, minus, we have a numerical coefficient of 1/3, so write it outside the integral sign. So 1/3 integral of sine of 3x dx. Okay, but we need to complete the differential so that we can apply the formula for integration of sine. So the differential part should be the complete differential of 3x. So therefore, there should be 3 there. So 3 dx. So since we put 3 in here, so outside we must multiply again 1/3. Okay. So this will be equal to 1 over 3x sine of 3x minus, so 1/3 times 1/3 is 1 over 9. Integral of sine is negative cosine. Since we finished integration, so plus c. Okay, so therefore our integral, so the integral of x cosine of 3x dx is equal to 1/3 x sine 3x plus 1 over 9 cosine of 3x plus c. Okay, so this is our integral. Okay. So I mentioned earlier that what if we made a mistake in assigning the u and du in our integrand. Okay. So let's solve it here in the remaining space. So we have integral of, so what will happen if for our integral of cosine 3x dx, so what will happen if we assign the wrong variables, no, for the parts u and dv? So what if our u is cosine 3x and our dv is x dx? Okay, so obviously we'll need our du. So our du is differentiate cosine 3x. So differential of cosine is negative sine 3x times differential of 3x, so 3 dx. So our du would be negative 3 sine 3x dx. Okay, so on the other hand, our dv would be our dv is x dx. Okay, so therefore our v would be the integral of this, so integral of x dx. So our v would be 1/2 x squared using the power formula. Okay, so using the integration by parts, so the formula was uv minus integral of v du. So u times v, so cosine of 3x times 1/2 x squared. Okay, so this is our u and then this is our v. Okay, looking good so far. Minus integral of v du. So our v is 1/2 x squared. Our du is 3 sine 3x, negative 3 sine 3x dx. Okay, so as you can see, so even if we simplify this, so this will become 1/2 x squared cosine 3x, and then this will become, so negative 3 times 1/2, the negative outside, so plus 3/2 integral of x squared sine 3x dx. Okay, so what have you noticed? So the integral part here got more complicated, okay, compared with our original integrand. Okay, so in our original integrand, the coefficient of the exponent of x is only 1. Here, it became 2. Okay, so therefore our integral became more complicated. Okay, and if we use another integration by parts here, no, using x squared as our u, then it will get more and more and more and more complicated. Okay, so therefore it is very important to know what variables, what parts of the integrand should we assign as the u or the dv. Okay, and again, the general rule in assigning u is this. Okay, so prioritize first the logarithmic, and then inverse trigonometric, and then algebraic, trigonometric, and then last option for assigning of u is the exponential function. Okay, so let's have another example. So for our second example, so we have the integral of y ln of y dy. Okay, so we will integrate this by parts. Okay, so we will have to select which one would be our u and which one would be our du. Okay, so comparing again with our general rule. Okay, so in assigning our u, so we will prioritize first the logarithmic. So we have here algebraic for y, and then for l and y, that is logarithmic. Okay, so therefore we will assign l and y as our u, and then the remaining y dy as our dv. Okay, so rewriting this, so we will have integral of ln of y times y dy. Okay, so here we will assign our u as, so our u will be equal to ln of y. So obviously our du is the differential of l and y, that would be dy over y. Okay, and then our dv is y dy. Okay, so therefore our v would be the integral of this. So using the power formula, we have 1/2 y squared. Okay, so applying the integration by parts, so here we will have, so from the formula, integral of u dv is equal to uv minus integral of v du. So u times v, so ln of y times 1/2 y squared. So this is our u, and then this is our v, minus integral of v multiplied by du. So we have dy over y. Okay, so this will become 1/2 y squared ln of y minus, so this will become 1/2. Okay, the numerical coefficient, take it outside of the integral of, so as you can see, we can cancel, so y squared over y, so we have y, and then dy. Okay, so integral of y dy, so similar with what we did here, so it's 1/2 y squared. So 1/2 y squared ln of y minus 1/2 integral of y dy is 1/2 y squared. Okay, so since we've done integrating, so plus c. So therefore, final answer is we have 1/2 y squared ln of y minus 1/4 y squared plus c. Okay, so for our third example, so we have the integral of x cubed e raised to negative x squared dx. Okay, so from the rule in integration by parts, so this is still in integration by parts, obviously. So again, we will use the rules, in selecting our u, in assigning our u for the integration by parts. So we have here algebraic for x cubed and then exponential for e raised to negative x squared. So here, obviously, we will be assigning the algebraic as our u. Okay, but however, we should be careful in assigning u and dv, because we have to make sure that our dv can be integrated. Okay, so here, if we assign directly our x cubed as our u, then what will be left for dv will be this, so e to the negative x squared dx. Okay, and we can't integrate it because, as you can see, the differential part should be the complete differential of the exponent of e, and the exponent of e is negative x squared. Okay, so therefore its complete differential should be negative 2x dx. Okay, and if we already assign our x cube, our u as x cube, then there will be no x left, no, to partner with dx. So we have to be careful of that. So to for us to be able to integrate dv, therefore the dx here should have a variable of x. So we will get 1x from x cubed, so that what will remain will become x squared e to the negative x squared, and then the 1x separated from x squared will be written here x dx. So in that way, our dv, our assigned dv, can now be integrated. So by parts, our u is x squared, therefore our du is 2x dx, and our dv is e to the negative x squared, and then multiplied by x dx. Okay, so to solve for our v, we need to integrate e to the negative x squared x dx. So for us to apply the formula for integral of exponential functions, then the differential part here should be the complete differential of the exponent of e. So the exponent of e is negative x squared. So therefore, its complete differential should be negative 2x dx. So therefore, we must write here negative 2. So outside the integral sign, we will write 1/2. So therefore, our v is negative 1/2 e raised to negative x squared. Okay, so applying that in our applying the integration by parts in our integral, so this will become, so the integral of x cubed e raised to negative x squared dx is equal to u times v. So u is x squared, v is negative 1/2 e raised to negative x squared minus integral of v du. So our v is negative 1/2 e raised to negative x squared. Our du is 2x dx. Okay, so as you can see, so we can simplify this. So we have here negative 1/2 x squared, okay, e raised to negative x squared And then, so similar here. So for us to integrate later, it should be negative in here. Okay, so the negative here, we can transfer here. And then the 1/2, we can take it outside the integral sign. So minus 1/2 integral of e raised to the negative x squared, and then negative 2x dx. Okay, so the differential part is already complete. Therefore, this will become negative 1/2 x squared e to the negative x squared minus 1/2 e to the negative x squared plus c. Okay,